Now, let us discuss about the joints. What are joints? These are the movable components of the robot that cause relative motion between the adjacent links. So, as we see here, there are 6 different types of joints. They are revolute, prismatic, screw or helix, cylindrical, spherical, and planar joints. Now coming to degrees of freedom. So what is degrees of freedom actually mean? The number of independent coordinates required to completely specify the relative movement of a robot is called a degrees of freedom. Nowadays, most common types of robot manipulators are serially connected spatial open kinematic chains. So for a spatial linkage, degrees of freedom is given by F is equals to 6 into n minus 1 minus 5 into R plus P plus H minus 4C minus 3 into S plus P dash, where n is given by number of links, R is for revolute pair, P for prismatic pair, H for skew or helix pair, C for cylindrical pair, S for spherical pair, and P for planar pair. Now let us discuss the degrees of freedom for various joints. Coming to the revolute joint. The relative rotation between the elements can be expressed by a single coordinate theta. Hence, a revolute joint has single degree of freedom. Next, coming to the prismatic joint, the relative translation between the elements can be expressed by a single coordinate L. Thus, it possesses 1 degree of freedom. Next, screw or helix joint. It has 1 degree of freedom since the relative movement between the elements is expressed by a single coordinate theta or L. These two coordinates are related. That is, number of rotations is related to the distance moved by the link. Hence, screw pair has 1 degree of freedom. Next, coming to the cylindrical joint, it has 2 degrees of freedom because it allows both rotation and translation parallel to the axis of rotation between the connected elements. These relative moments can be expressed by two independent coordinates theta and L. Next, coming to the spherical joint, a ball and socket joint forms a spherical joint. This connection has 3 degrees of freedom. Since the complete description of the relative movement between the connected elements needs 3 independent coordinates. Next, coming to the planar joints. A planar joint has 3 degrees of freedom. 2 coordinates describe the relative translation and the third coordinate describe the relative rotation. Now let us discuss about the workspace. What is workspace? This is a set of points that can be reached by the end effector of a robot. So to increase the workspace, we made the torso sliding. With increasing joints, flexibility of the robot increases and workspace also increases, and also the complexity of inverse kinematics gets increased. We shall discuss the topic of inverse kinematics later in this video. Now Ishwar is going to add joints for the fetcher bot.
Hi guys, as Joshika has completed the part of explaining the joints and the degrees of freedom of the system, so I'll be continuing by making the joints of the hand. Okay, so first let's make a semicircle of radius 50. Yeah. Um, so yeah, this part is a semicircle. These are two semicircles. So I'm going to extrude half of it to a height of 120 mm. As you can see, yeah, this is the part. So I need to make a sketch this side, as this construction is, yeah, I've just make it invisible. Okay, so I'm making the circle here in a sketch, and this circle should be extruded 10 centimeters to the upward and 50 centimeters to the backward. So first I'll be extruding the 10 centimeters, and I'm selecting the operation join, then okay, then again I'll extrude this is this to minus 50. So basically when we use this minus thing, it will come as cut, so we can change it as join, and then it gets joined, and we can click OK. So if we remove this, yeah, this is the structure which we are going to attach to. This would be attached to, making the component visible. This would be attached here. As you can see, we'll be having a rotating joint. It would be attached here, so which increases the motion of the hand. So a part like we need three parts like this. So as this one is a body, I'll make it into a component, and from the component I'll be mirroring it. So for mirror, we should just search. We have to click S so that we get a search bar. We can type mirror. We'll get the mirror option. So we can capture the present positions. We have to mirror the components. So I've selected components. This is the component, and mirror plane would be anything. We can take even this one. Yeah, so we got a mirror. Okay. So I'm moving this component from here, and again I'll be doing mirroring because we need three, right? This one is a mirroring plane. Yeah, done. So as we needed three parts, we are done with them. And yeah, just a second. We need two small, what to say, cylindrical type of surfaces. So we'll again model them. So it's of the same radius, and this time we have to extrude it by 20 mm. Oh, okay, we'll extrude by 30. It would be looking better, I feel. So yeah, as we have made it, I'm turning it into a body, it into a component, and as we need to, I'll be mirroring it again. Yeah. So this is the component. This is the mirror plane. Yeah, done. So these parts are ready. We have to make two more hands type of thing. So I'll sketch them again. Capture position. Each time I'm applying capture position because when we capture the position, we'll get the parts as it is in the place they are. Or else if we just click continue, it will come to the position initially it was. So this would not this would disturb the space we created for our sketches. For that, I'm doing that thing. So same case as before. I have to make a semicircle of radius 50, and then I have to extrude it to 120 centimeters. Sorry, 120 mm. And after extruding it, I have to sketch this side. As this component is again coming in our way, we can just make it invisible. I'm doing the same in the above case, but there will be a small modification. I'll just show you guys. For extruding it, I'll take 10. Yeah, join. And again, sorry, this minus 50. I have to make it join. And okay, in this sketch. Hmm. Now we have to extrude this by 20, or minus 20. Okay, so this is the part we had to make. I'll turn it into a component. So yeah, this is another component. We have to mirror this again. For mirroring, as we know, okay, so we are left with modeling two things, an end effector and a part connecting it. So let's first create a part connecting it. It's the same circle, it's a circle of the same radius, but a small thickness. Sketch. So I'm making it 10 mm thick, or maybe make it 15. It's done. Let's create it into a component. Yeah, it's done. We can remove it. We can place it aside. While creating joints, we'll be attaching these. So now I'll create the end effector. So the dimensions of the end effector were, just a second, 105 into 80. So 105 here, 80 there, and it has a height of 60. So I need to offset the plane for constructing another part. So offsetting the plane. Offsetting this plane by height of 60. Yeah, done. So now I'll be sketching on this plane. This time I'll create a rectangle with center. So this is the center we want. From there, the dimensions are 120 and 90. So this side 120, the other side it's 90. It's made. Now we have to loft this one. Lofting means when we select two surfaces, I'll show you guys. This is the two profiles. So this is lofting. When we select the surfaces, they get attached and become a solid. So it's a new body. Okay. This is the loft we wanted to create it. Okay. Mm. And on this, we have to add two holders. So for holders, we have to make a small cut. For cut, I'm choosing a rectangle, center based rectangle. Its dimensions should be smaller than this one. Just a second. I have not chose the center. It should be 30. Yeah, so something like this. And then I'm extruding this part. I'm cutting it to minus 10. So you're getting a cut feature and okay. So I had to make this because I needed to cut in the middle. So in this total length, we have to keep two holders. So holder pins, yeah. So I'll create a sketch here. This maybe I can say I'll start at this point. And as a total length, you can observe it as 115. So I'll create small hinges at 40 maybe. And same this side. I'll take something at the distance 40 and choose a rectangle based on the center. Its width should be 10. Yeah. So let's extrude this one. I have to extrude it for 55 mm, and it should not join, it should be a new body, or maybe I can say new component. Yeah. And the same as the next one, 55, new component. We can hide the sketches. I just wanted to make the ends of this smooth. So for that, we can use the function fillet. So for filleting, we have to select the edges, and specify a radius of maybe I can say 2 or maybe 3. That would be fine. So now you can look how the fillet function works. It just makes it smooth on all the sides. Yeah, so I'm converting this body also into a component now. So as we can see, we have all these components now. We can first fix them and then we'll be coloring them. As you guys know about joints, I would first fix a rotational joint here. So between this one and this one, so it would be a revolutionary joint. So in this I can hit 90 degrees maybe. Yeah. And then we have to attach the small piece which we have made. This one. Between these and this. So that was a small mistake. Let's join. I'm making another rotational joint here. Okay. now I'll attach this point, this component with uh, here. So this joint should be rigid. Okay then. And after this, I have to join the third piece to it. Third piece means, yeah, this one to it, to this one. So S joint, and this should be a rotational joint. Yeah. And now I have to attach a small piece to it. This one. That too rigidly. Capture positions. Now we have to attach these two parts here. Just a second. Head to a rotational joint. Yeah. And to this one, we have to again attach rotational joint. That is this one. We are left out with two pieces. This one we have to attach it here, and to that one we have to directly attach the end effector. this one is going to attach to it rigidly. So let's join position, rigid one. Okay, and this also gets attached to it rigidly. Before that, we can do one thing. While making it, I've made I've made these as separate components because the holder pins need to move from here to here maybe. So for that, I'll create a slider joint. Yeah. So S joint. Yeah. So I fixed the slider joint. For this also I'll be fixing the slider joint. So I'm selecting the joint for animating the joint. Yeah. So this is the animation. Okay. So this is the way these end effectors work. Uh, I'll be attaching this one to that rigidly. Yeah, so this is the whole system. As you can see, this one is called end effector. So you can see there are many revolutionary joints and rigid joints in the middle. So we'll be grounding this component, the base component. Grounding means it stays constant in its place. So once it's grounded, everything moves as it's constrained. You can see I can play with these joints like this. This can move like this. This can move. So overall, I can. So as you can see, you can turn all these and make such that this end effector reaches a specific position. So end effector is also known as yeah, it's a device used in the robotic arm. So it only interacts with the environment rather than the hand, other joints and all. So end effector is the one which interacts with the robot. Sorry, which interacts with the environment. So comparing it with the human hand, we can say it is like palm maybe, or the fingers. So it generally grasps and manipulates the objects in the way which we want. So the holders are also known as robotic grippers. So there are many types of robotic grippers used. So these can be mechanical, pneumatic, magnetic. So it's based on the type of the robots we use. So now let's do coloring. Appearance. So in appearance, I'll be using this one.
Now we are going to discuss about the forward kinematics. So before going to the topic, let us discuss about the actuators and servo motors. So what are actuators? These are the devices that actually move the robot joints. It is a device that causes motion, and it can cause linear motion or rotatory motion. Next, servo motors. These servo motors are widely used in robots. These are the electronic devices and rotary or linear actuators that rotate and push parts of a machine with precision. These are mounted in every joint of a robotic welding arm, actuating movement. They have many advantages such as high efficiency, high accuracy, smooth running, small in size, and well suited to varying load applications. Next, coming to the forward kinematics. Most of the industrial and other robot manipulators are based upon an open kinematic structure with the operational unit called the end effector or gripper placed at the end of the open chain. The primary objective of a manipulator is to place the end effector at a desired location and orient it in a desired manner. There are two basic problems in kinematics of open chains. First is to determine the position and orientation of the end link for the given joint variables known as the forward kinematics. Next is to determine the joint variables when the position and orientation of the end link, that is the end effector, are prescribed, and it is called as the inverse kinematics. So coming to the forward kinematics, we have matrix method which we use to solve. Matrix method is also called as the Dinavit-Hertenberg or HT method. In this method, a Cartesian coordinate system is attached to each link. The coordinates of a point in the space expressed in two such coordinate systems are related through a 4x4 matrix called the homogeneous transformation matrix. Here I am taking this example and defining four variables. First is length of the link I. It is denoted as Li. It is the mutually perpendicular distance between the axis I minus 1 and axis I. Next, angle of twist of link I, which is called as the alpha I. It is defined as the angle between the axis I minus 1 and axis I. Next, SI, which is the offset of link I. It is the distance measured from a point where A minus 1 intersects the axis I minus 1 to the point where AI intersects the axis I minus 1 measured along the z-axis. Next, we are defining the joint angle theta I. It is defined as the angle between the extension of AI minus 1 and AI measured about the axis nodes I minus 1. Here I is defined as the links like 1, 2, 3 and so on. So here the homogeneous transformation matrix is defined as AI, which is equals to the cos theta I minus cos alpha I sin theta I sin alpha I sin theta I Li cos theta I sin theta I cos alpha I cos theta I minus sin alpha I cos theta I Li sin theta I 0 sin alpha I cos alpha I Si 0 0 0 and 1. Here, the matrix AI represents the description of the I plus 1th coordinate system in the ith coordinate system. Now, the position and orientation of the n plus 1th coordinate system is represented as Tn is equals to A1 into A2 into A3 and so on An. Here in this example, we have 6 revolute joints. Hence, the transformation matrix is written as Tn is equals to, that is T6 is equals to A1 into A2 into A3 into A4 into A5 into A6. Thus, we obtain the matrix in the O dash coordinate system with respect to the points that are determined in the O coordinate system. That is the reference coordinate system. Here the final matrix is A, which is given by xx, yx, zx, px, xy, yy, zy, py, xz, yz, zz, pz and 0, 0, 0, 1. Here we have three unit vectors which are defined as x is equals to xx I cap plus xy j cap plus xz k cap, y is equals to yx I cap plus yy j cap plus yz k cap, and z is equals to zx I cap plus zy j cap plus zz k cap. These unit vectors represent the direction of the axis x, y, z of the new coordinate system. The vector p is equals to px I cap plus py j cap plus pz k cap represents the location of the origin of the new coordinate system O with respect to the reference coordinate. Hence, comparing the elements of Tn with those of A, the location of the origin and the direction of the axis x, y, z are obtained. Now, going to inverse kinematics, as we discussed earlier, inverse kinematics is to determine the joint variables when the position and orientation of the end link, that is, the end effector, are prescribed. Inverse kinematics is rather complicated compared to that of forward kinematics. And here we have two different approaches to solve the inverse kinematics problems. First one is analytical solution, which is used to solve the problems in closed form. Here we use ad hoc geometric inspection and algebraic methods. Next, three consecutive rotational joint axes which are parallel are the sufficient conditions. And next we have the numerical method. Numerical methods can be used to find a solution to the inverse problem if a closed form solution does not exist. Here, inverse kinematics is not that much important. We concentrate just on forward kinematics. Thus, so far we have discussed about the forward kinematics. Now let us discuss about the degrees of freedom. Let us calculate the degrees of freedom of two robots, Fetch robot and the Puma 560 model. As we calculated the formula for degrees of freedom, f is equals to 6 into n minus 1 minus 5 into r plus p plus h minus 4c, and some other terms are there. Here revolute and prismatic pairs are enough. So for taking Puma 560 model, here we calculating the degrees of freedom. So as we see here, it is the link 0, and here this yellow one is link 1, and this one is link 2, and here it is link 3, here it is link 4, and here it is link 5, and here the gripper is the link 6. And next we shall calculate the number of joints. Here there is one joint, 1, and here it is 2 revolute, second joint, and here it is 3 again revolute joint, and then here fourth joint, here fifth joint, and then here sixth joint. So there are total number of 6 links and 6 joints. So keeping it in the formula, f is equals to 3 into n minus 1, f is equals to 6 into n minus 1 minus 5 into r plus p plus h. Upon substituting in it, we get 6 degrees of freedom. So here we use the matrix method which we discussed earlier, and we write the transformation matrices A1, A2, A3, A4, A5 and A6, and finally we get the transformation matrix T6, upon which we can determine the location and the orientation of the end effector. Now here we got the 6 degrees of freedom for the Puma 560 model. Similarly, when we calculate for the Fetch robot, we get 7 degrees of freedom. So here now, up to now, we have discussed about the degrees of freedom, how to build a robot in Fusion 360, and then how to apply the forward kinematics, and a bit knowledge of inverse kinematics. So now I hope you got some idea about this robot stuff and how to design it and find the number of degrees of freedom of the robot. Okay, thank you.